Okay, continuing on, we're now looking at the spatially oriented eigenvalue of Schrödinger's equation. Again, we separate variables. We set it equal to the eigenvalue, which is minus beta squared, some constant. I have placed V, this constant, denoting the amount of energy of the electric field of the proton, which the electron has to move through, as V. I've put it in the x, along with the x eigenvalue, since I'm just choosing x as a preferred direction. The photon comes in, strikes the electron, moves it through, and so forth. So you could use y or z or any combination. You will get exactly the same answer. So we now have this part of the equation, x double prime over x plus v is a constant equal to minus beta squared. Rearranging, we get this value here. And then solving this particular differential equation using the cosine part of the solution, so that we have x, which is a function of x only, is equal to the cosine of this value, the square root of twice m times bracket v plus beta squared, all divided by Planck's constant divided by 2 pi, which is multiply times x. Rearranging this part here, this will be equal to 2 pi, which would then make x equal to 1, or this value would all be 1 if this value was equal to 2 pi, which would happen when x is equal to this particular value. Also, it would be equal to 1 when x is equal to 0. So we now have this particular condition that would set the boundary condition so that x would also be equal to 1, psi would equal to 1 as well, which would combine nicely with our time-oriented boundary condition. So they're both equal to 1. 1 times 1 is equal to 1. So we add here, using this comes from this part of the equation for the momentum squared. Momentum squared would equal this part. We set x equal to 1. That's now equal to 1, making this equal to x squared, x double prime. X double prime would come from this equation here. Substituting in, we have p squared equal to this part here, so that p, taking the square root of this, is now equal to this part. So we now have x is equal to 2 pi times h bar, which is just h, Planck's constant, divided by the momentum from here, which is p. Rearranging, we now have x will have, yes, make it look right, p times x would equal h, which is our boundary condition that would make this function in x only, or the x-oriented function, equal to 1, which would give us p times x equals h. So we'll put that in as the spatially oriented boundary condition. P times x equals h, and if you substituted for either y or z, you would get exactly the same answer using this particular technique. So these are both the time-oriented and the spatially oriented. The time-oriented boundary condition is et equals h, and momentum times x in the spatially oriented would equal also Planck's constant. So there we have the boundary conditions of Schrödinger's equation, such that we have where psi is equal to 1 at the boundary.